Welcome to the 7th of 14 videos on the arc flash truth no one explains. My name is Joe Chacon. I'm the president of Podge LLC and Chacon Engineering. I'm a licensed professional engineer in multiple states and have been an electrical engineer for almost 30 years. Please like and subscribe as this helps us get this important information in front of more people. This video is going to walk through a medium voltage example for incident energy calculation. Low voltage is similar. I encourage you to look back at the previous 6 videos, even though this video stands on its own. We will be doing a lot of math in this video, so buckle your seatbelts and let's get started. The IEEE standard requires calculation of something they call intermediate incident energy, which is an exponent logarithmic regression equation with a rational 7th order polynomial term. I think the best way to look at all the governing equations from the standard is with an example. Remember the example from the previous video. We'll continue with that. 508 millimeters by 508 millimeters by 508 millimeter enclosure, deemed by definition to be typical and not shallow. Working distance will be 18 inches. Bolted fault current is 60 kiloamps. Voltage is 690 volt. Clearing time is 200 milliseconds. Let's make the electrode or bus bar gap 1 inch or 25 millimeters. And the bus bar configuration is all vertical, called VCB. The first thing we have to do is calculate the intermediate arcing currents. The standard refers to these as IARC 600, IARC 2700, and IARC 14300. They correspond to 600 volts, 2700 volts, and 14,300 volts respectively. I think it's weird, but that's how the standard teaches it. Remember, they had to empirically derive all of this. Take a look at the first equation, which is called IARC 600. Notice the coefficients K1 through K10. You get the IARC 600 coefficients from table 1 in the standard. Make sure you pick the row corresponding to VCB. For our example, this is what the equation looks like after plugging in all the values. The solution is 39.280 Ka for IARC 600. The second equation is called IARC 2700. Again, the K1 through K10 equations are in table 1. This is what the equation looks like after plugging in all the values. The solution is 50.845 Ka for IARC 2700. The third and final intermediate arcing equation is called IARC 14,300. Again, K1 through K10 are in table 1. This is what the equation looks like after plugging in all the values. The solution is 56.054 Ka for IARC 14,300. You are free at this point to calculate actual arcing current by these 4 equations if you so desire. It is not necessary to calculate incident energy, though, except knowing that the clearing time of the upstream overcurrent protective device. Only the intermediate arcing currents are needed for these calculations. Note, I use the word actual arcing current, but you will see in a bit there is an additional step to get the true actual arcing current. Remember, everything is empirical, therefore there are all these corrections that the standard uses. We also need to calculate something called the equivalent enclosure size, called EES, and then correction factor referred to as CF. This can be quite burdensome. Table 6 in the standard defines all the logical parameters to calculate what they call width 1 and height 1. The EES, or enclosure size correction factor, is simply the average of this width 1 and height 1. Then CF can be calculated with this equation, but only if the enclosure is deemed typical and not shallow. We're almost there to being able to calculate incident energy. Let's take a look at the first equation called E600 for incident energy, which also has an intermediate step. Notice the coefficients K1 through K13. You get the E600 equations from table 3. Make sure you pick the row corresponding to VCB. The solution is 83.77 joules per centimeter squared. The second equation is called E2700. The K1 through K13 equations are in table 4. The solution is 144.72 joules per centimeter squared. Third and last equation is called E14300. The K1 through K13 coefficients are in table 5. The solution is 158.75 joules per centimeter squared. We take the intermediate incident energy values of E600, E2700, and E14300 and interpolate actual incident energy with these equations. We end up getting 88.78 joules per centimeter squared. That can be converted to calories per centimeter squared, which computes to 21.22 calories per centimeter squared. At this point, we need to account for arcing current variation. The standard calls this var CF. VARCF. This is necessary to determine if the arcing current variation has an effect on the clearing time on the upstream protected device. This equation has 7 coefficients called K1 through K7 that can be found in tables 2 of the standard. Remember, pick the VCB row for our example. The computation shows that VARCF is 0.2250399. We now have to adjust our IARC 600, IARC 2700, and IARC 14,300 values with this correction factor. We multiply each one respectively by 1 minus 0.5 times the VARCF. These are the corresponding equations. They're called IARC 600 min, IARC 2700 min, and IARC 14,300 min, respectively. We interpolate these as we did before, and we get 35.687 Ka. Recall, our previous solution before applying this VARCF correction factor was 39.280 Ka. This means our 200 millisecond clearing time is not really accurate, which is why we apply the VARCF correction factor. That is, we need to know how the true arcing current affects clearing time. I am not going to show you how to calculate this clearing time, but simply say you'll need to pull up the time current curve, or TCC we call it sometimes, for the upstream overcurrent protected device. I did that for our example and calculated that time to be 225 milliseconds, which is a little bit slower than 200 milliseconds. So what we have to do at this point is recalculate E600, E2700, and E14300 again for the new clearing time and new IARC 600 min, IARC 2700 min, and IARC 14,300 min. The equations are exactly the same as before. When we plug those values in, we get 58.449 joules per centimeter squared for the new E600, 132.858 joules per centimeter squared for the new E2700, and 207.752 joules per centimeter squared for the new E14300. We then need to interpolate as we did before. That computes to 64.13 joules per centimeter squared, or 15.33 calories per centimeter squared. Notice the incident energy is a little bit less than 21.22 calories per centimeter squared, which is what we calculated before we applied the VARCF correction factor. This is not always the case, and why performing this VARCF correction factor is important. Sometimes the incident energy is higher because the clearing time goes up significantly. Be careful, just be careful. Let's review this process one more time for medium voltage. Number 1, calculate intermediate arcing currents, IARC 600, IARC 2700, and IARC 14,300. Number 2, determine the overcurrent protected device clearing time in milliseconds based off interpolating IARC 600, IARC 2700, and IARC 14,300. Number 3, calculate the enclosure corrections EES and CF. Number 4, calculate the intermediate incident energies E600, E2700, and E14300. Number 5, calculate the arcing current variation correction factor. Number 6, recalculate the intermediate arcing currents at IARC 600 min, IARC 2700 min, and IARC 14,300 min by applying the arcing current correction variation factor. Number 7, redetermine the true overcurrent protective device clearing time in milliseconds based on the updated IARC min and interpolating IARC 600 min, IARC 2700 min, and IARC 14,300 min. Number 8, recalculate the intermediate incident energies E600, E2700, and E14300 with the updated clearing time and IARC 600 min, IARC 2700 min, and IARC 14,300 min. And number 9, interpolate the actual incident energy from the recalculated E600, E2700, and E14300. Almost nobody does this math manually like this. We use software packages like EasyPower, SKM, or ETAP. But I do think it is important for every engineer who uses these software packages to know where the math comes from and at least do some by hand just for practice. The next video will focus on the arc flash boundary calculation for this same example.